Yes, there was a network issue. Sorry for that. We were discussing about the nullity of a matrix. And of course, we mentioned that basic ingredients to understanding the nullity of a matrix is to remember that you consider a homogeneous linear system in which you consider the set of solutions of the homogeneous linear system. Said that the set of solution of this homogeneous system form a vector space or vector subspace. And this vector subspace is called the null space. We then further mentioned that the dimension of the null space has the name, the nullity of A. And what is the nullity of A? It was mentioned that the nullity of A is simply equal to the number of columns of A minus the rank of A. Now let's consider an example to clarify what we mentioned. This example, we are going to consider evaluating the rank of a matrix and also evaluating the nullity of a matrix. So suppose we are to evaluate the rank and nullity of the matrix. Which matrix? Of the matrix 2, 16, 4, 2. I have 4, 8, 8, 16. I have 8, 4, 16, 8. I have 16, 2, 2, 4. Now, we have this theorem of us solution. Let's consider the solution. First, we would like to obtain the rank of this matrix. And instead of going by the way of trying to look for the number of linearly independent, the approach used in the previous lecture, that might take some time. Why not go by the echelon row reduction that is considered here? So let's see. Using the echelon row reduction, so we want to consider the matrix. Let's write it again. 2, 16, 4, 2. We have 4, 8, 8, 16. The next one is what? We have 8, yes, 8, 4, 16, 8. So we have 8, 8, 4, 16, 8. And then next one is 16, 2, 2, 4. Now, following the echelon row reduction, we can say row 2 minus, what do you think? Row 1. Yes, row 1. If you think row 1, you are correct. So let me reduce the size of this. Yes. Okay. Now, let's write it here. We have 2, 4, 8, 16. And here we'll be using this formula that we have here. We expect that this will be 0, 8 minus 8 times 4. You observe that this is minus 24. 4 minus 8 times 8, we are going to have minus 60. 2 minus 8 times 16, we have minus 126. And come here, what do you observe? We have, you can say row 3 minus 2 row what? 1, 2 row 1. We do that, we can have here, let me clean it properly, write properly. We have 1. So we can have here, we observe that what we have here will be 0, and then if you look at it here, 8 minus 2 row 1, that is minus 2 times 4, which is 8. We have 0 here, and row 3 minus 2 row 1, 16 minus 2 times 8, we also have 0 here, and lastly 2 minus 2 times 16, we observe that we have minus 30. And for the last row, we can say row 4 minus row 1. What do you observe? Here will be 0. 16 minus 4, we have 12. 8 minus 0. 4 minus 16, we have minus 12. Okay, now can we proceed further? We can proceed further. We observe here that this, if you consider the last two, I can use the formula 2 row 4 plus row 2. And if I do that, I'm going to have 2, 4, 8, 16. Here I will have 0 minus 24, I have minus 60, I have minus 126, 0, 0, 0, minus 30, and here I will have 0, 12, 2 times row 4, that's 2 times 12, I have 24, plus row 2 now, which is minus 24, I have 0. And then next, you observe that if I do the calculation, 0, we have plus minus 60, I have minus 60 here. And then I have 2 times minus 2, that's minus 24, and then minus 126, and that will be minus 115. Of course, I can change row, I can switch row. Okay, it doesn't affect the rank. And of course, this, if I do, I will have the following. Let me just indicate an arrow. I have 2, 4, 8, 16. I have 0, minus 24, minus 60, minus 126. And here I have 0, 0, minus 60, minus 150. And I have here 0, 0, 0, minus 30. You notice that I've been able to successfully reduce the matrix to a triangular matrix. And of course, having a triangular matrix this way, it implies that the row vectors are linearly independent. If I can successfully reduce the matrix to a triangular matrix of that form. So it is clear that the maximum number of linearly independent vector that I have in this matrix, which is equal to the rank of the matrix, is simply 4. Is simply 4. The question is, what then is the nullity of the matrix? As I mentioned, the formula nullity is equal to nullity of the matrix. I'll simply write nullity. Nullity is the number of columns of this matrix, let's count the columns. 1, 2, 3, 4. 4 columns minus the rank of the matrix. How many? 4. So 4 minus 4, the nullity will become 0. The nullity will become 0. And it is as simple as that. All right. Now is time for the second exercise. So let's have the exercise, and I'll call it assignment 2. Yes. Please ensure you submit this assignment via the Google platform. It will be good. Now, 1 is that determine the ranks and nullities of the following matrix. Roman figure 1, we are given 0, 1, 3, minus 2, 1, 0, 7, 4. We have 5, 5, 5, 5. Then 2, you have the matrix to deal with. 1, 1, 2, 1, 2, 1, 2, 1, 1. You can write that. We are to determine the ranks and nullity of the following matrix. Now we move on to the second one. Roman figure 2. Oh, sorry, number 2, pardon me. Number 2. Suppose we are told that given that A and B are matrices with non-zero entries, show that one, the rank of B transpose A transpose is equal to the rank of AB. Roman figure 2. We are to show that rank of A equals rank of B will not mean, or let me write it as does not imply that rank of A squared is equal to rank of B squared. Okay. Here, you only need to provide a counter example in this Roman figure 2. The counter example will suffice. Then number 3. Number 3 is that what is the rank of matrix A whose component or whose entry AIG satisfies, that's each entry now satisfies this formula. AIG is equal to 2 raised to power I plus j minus 2. We have here I comma j is equal to 1, 2, 3. 1, 2, 3. Yes. Now, that is that for you. Please try and do the assignment. Let me reduce the screen so that you can see what is needed to be done. Okay. So this, all right. The next topic that we are going to consider in another lecture will be determinants. Determinants. There we are going to see how to evaluate determinants, see some properties of determinant. Can you use determinant to evaluate the rank of a matrix? Yes, you can. We will see that in the subsequent lecture. Thank you very much for listening.